Yeah, good morning, everybody. You're welcome to Math 001. I'm sorry that I've not contacted you for a bit. Okay, I can confirm to you that my trip to the United Kingdom was smooth, and the country is a little bit cold at the moment. So I've practically spent like a couple of my early days sleeping, and yeah, now I can remember you. So we're going back to we're starting with Math 001, 001, and it, I think we should continue with our partial fraction. So it's let me see if I can divide the screen into two. Okay, and say partial fraction continuation. Okay, we'll continue with a partial partial fraction. So I think I want to move back a little to where we have dealt with. Then we can now move to where we have not. So, like, let me create a bridge between what we know and what we do not know, using what we know as a bridge. The last thing we dealt with. So let's discuss it. So I'm going to pick this example, which says 3x raised to power 2, 3x raised to power 2 plus 8x plus 13, everything over. Now let me go as slowly as possible. X minus 1 and x squared plus 2x plus 5. All right, when we take a good look at this, we can see that the denominator, we have two denominators. We have we have two denominators, one which is a denominator which is linear and one which is quadratic. So if you look at the quadratic one, you can see that we can't quite um, factorize that because I can't think of any two numbers we will multiply to give me 5, such that when we add them, those numbers, they will give us 2. So practically, that other parts of the denominator cannot be simplified. So I remember that we said when we have situation like this, we can go on safely by saying this is the same thing as okay, this is the same thing as let's put equivalent here to okay, x plus 1 as the first denominator. We put a on it, we'll explain that later, and x squared plus 2x plus 5, which is the second denominator. Now, we are putting a here because it's a constant, and we're choosing that as a constant. We're choosing that constant because we know that x plus 1, which is the denominator, is actually linear in nature. So if it is linear in nature, then what do? We select a constant as the numerator because we want a fraction, a proper fraction, meaning that we have something smaller at the top and something bigger at the base. And definitely um, constant comes before a linear. Like you would find a constant in a linear expression. Every linear expression has a constant. So that's that. Now here, this is a quadratic expression which cannot be factorized, which means that it contains a linear. So we first, where it contains a constant, it contains a linear. So to be on the safe side, we should just put a linear at the top. So to put linear now, we say bx plus c. We've discussed this one in the classes before. All right. So when we have a situation like this, what do? Now we can now add the two together. If we add it, so we have two fractions that we want to add. It means that we have to take the LCM of both. I told you when you are taking LCM and you're lazy about it, just multiply the two denominators. So we have x plus 1 times x squared plus 2x plus 5. So that is it. That's it. Now you can see that the denominator. Okay, then when you have done that, then the usual thing that the a here will multiply x squared plus 2x plus 5, and you add this to bx plus c multiplying the x plus 1. Okay, so well, now when we compare, let's compare this guy now and this guy. We can see that their denominators are the same. So if their denominators are the same, then it means that the numerators are also equal. So we can scratch the numerators now and just talk about the the denominators now and equate the numerators, or say that they are equivalent. So we now have 3x squared plus 8x plus 13, which is now equivalent to a into x squared plus 2x plus 5 plus bx plus c multiplying x minus 1. Okay, so we can now start killing. So killing can start now. So if we want to, we are looking for a, so why don't we just kill off b and c? Let me pick a cool color now. Let me pick a cool color. So yeah. So we want to eliminate b and c in order to find a. So now if we set x to be equal to 1. So if x becomes 1, then this is going to be 1 minus 1, which is going to be 0, as in here. So this is going to be 0. So it's going to kill off the entire stretch of what we have here. So we say set x to be 1. Then we are going to have 3 plus 8 plus 13, which is equal to a into 1 plus 2 plus 5, which means that this is 24 in, or is going to be the same thing as what's this guy now? Okay, 8a, which implies that your a is in fact what? 3. So we have found our a here to be 3. All right, we have found our a to be 3. Let's pick another color. Like I said, I want this thing to be as delightful as possible. Okay, let me pick that navy blue. Fantastic. So we have found a to be 3. Now let's take another look at it. Okay, let's say we want to find c. If we are looking for c now, then we can kill b by setting x to be 0. Now set x to be 0. Okay, here to kill b and c. To kill b and c. Set x to be 0 now. Specifically, setting x to be 0 will kill b. To kill b. Of course, we know what a is, so it doesn't really matter. A is 3 already, so we can just slide it in. All right, so we are now going to have something like so if we are setting x to be 0, so everything will be on this side, everything becomes just 13 equals, well, let's see, equals 13. A is 3 into what will be here, 5, because that's the only thing that will survive when x is 0, plus, okay, this is going to be, this guy is dead, this guy is c times minus 1. Okay, well, so this implies that we have 13 equals 15 minus c, which implies that minus c is going to give us what? Naturally, minus c is going to give us minus 2, which implies that your c is in fact 2. So we have found our c here to be 2. We have found our c to be 2. There's a problem that I always face when I use this tablet to write. I may not quite understand where I am again. Okay, now, okay, let me squeeze everything in the line beneath everything. Just follow what I'm doing and write these things out sequentially and make sure in your note, please, and make sure that it is neat. When I'm back, that's the first thing I'm going to ask about. So we have found C, we have found B. No, sorry, we have found A, we have found C. Now, how do we? What's left for us? Yes, how do we? Okay, there's no way we can damage C. There's no way we can kill C without killing B and C. B and A, or without killing B. So we don't have to bother. I think we can just call. Okay, let's call it. If we call it one, it will be bad. If we call it two, let's call it two. Let's call hex two. Set hex to be two. Set x equals. Let me put a line here so that you know. So from here you go here, and now from here you come to this place. All right, set x to be 2 to be equal to 2. All right, that would be something. That would be something. Okay, it doesn't matter. We'll do it. Okay. Oh, wait, why don't we even set, let me try. Let's set x to be 1 again. If we set x to be 1, then we are going to keep b and c. Okay, we don't want to do that. If we set x to be 0, okay, let's set x to be 2. Let's set x to be 2 and set b to be 3 and c to be 2. All right, so we do that in the expression, we are going to have something huge. I think you should go and finish that up. Please finish that up and let me know what you get. So finish it up on your own. I could have done it, but I think I just got lazy here. All right, so I'm going to save this page now so that I'm going to keep it for you later. All right, so that is gone now. We now want to discuss the last item for partial fraction, which is what happens when you have repeated bases. So I'm going to divide the screen into 2 again. Okay, yeah. Okay, it's skewed to the left, so let me clear it. Okay, let me just move it a little bit to the right and try as much as possible to make it as straight as possible. Okay, I think it's better. It's much better. All right, so okay, so at least now I know where I can go beyond. All right, fantastic. Okay, so now you have a situation. You have a situation where your denominator is repetitive. We call it a repetitive denominator. Excuse me. Let me find an example. Okay. Okay. Yeah. So let's say you have a. Let me just launch at an example straight up. Then I would, from the example, I will explain what I have to do, what we have to do. Okay, so this is good. This is really, really beautiful. Okay, 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 okay. 4x. So we are looking at 4x minus, oh sorry, 4 minus, sorry, let me clear that, sorry. Okay, 4 minus 2x. I think we've done this before. It's ringing a bell to me, but then let's just do it still, just to, okay, into x minus 1 into x squared minus 1 into x squared minus 1. Okay, so if we are to resolve this into partial fraction, all right, so resolve into partial fraction. Okay, if we are to resolve this into partial fraction, okay, let me just, okay, so when we, I think we have done this before, but let's just do it. So we have 4 minus 2x over x minus 1 times x squared minus 1. And we know that x squared minus 1 is a quadratic. But is x squared minus 1 factorizable? The answer is yes. That's the difference of two squares. So it's going to be 4 minus 2x over x minus 1, the first one. Now this second one is actually x minus 1, x plus 1. That's how it is resolved because it's different. So this is now actually the same thing as 4 minus 2x. When we bring this and this together, we have x minus 1 squared times x plus 1. Now in this situation, we now say we have repeated denominator because x minus 1 is coming twice. X minus 1 is coming twice. Now, how do we resolve this situation? Okay, let me say it's the same thing as 4 minus 2x. I want us to look at it the way we have been looking at everything, into x plus 1. Okay, x minus 1 raised to power 2. So this is the same thing. We can actually resolve this one, as we know that this denominator is cool, it's linear, it has no problem, we have no problem with it. So it's going to be a over x plus 1. That one is resolved. Plus, now, this is where the problem is. Well, let's put it on x minus 1 squared first. Okay, and put question mark on top of this place because we don't know what it is. So we'll come back to the question mark later. Now, when we look at, when we take a good look at x minus 1, how many factors do you think x minus 1 has? Sorry, x minus 1 squared. How many factors do you think x minus 1 squared have? Now, I'm going to, let me pick a color. This time around, I'm picking red. Let me pick this red. I don't know. Yeah, let me pick this red so that I can use it to explain. So, when we look at, say, 6, 6 has 2 as a factor, 3 as a factor. When we look at say 12, 12 has a factor of 2, it has 3 as a factor, it has 4 as a factor. Actually, this one also has 6 as a factor. Okay, now when we are looking at 12, we have 2, 3, 4, 6, and 12 as a factor. So when we look at x minus 1 squared, then we know it has a factor of x minus 1. It also has a factor of x minus 1 squared. Okay, so these are the possible factors of x minus 1. And all this we need to put into consideration, meaning that this guy here is not going to be like this. It's going to be in a two-fold. So actually, so we can now ring the whole of this and come here and rewrite this as a. You can say this is now equivalent to a over x minus 1 plus, what do we put on top of it? Let's put yeah, b over x minus 1 as well. Sorry, this is going to be plus. Yeah, that's going to be plus now c over x minus 1 all squared. We don't need to put this one as x plus, even though this is linear, but then we don't need to put it, we just need to put it as c. Okay, then when we've done that, we can now come down here and find the LCM. What's the LCM going to be? What's the LCM of this going to be? We don't have to multiply the 3. It's going to make it cumbersome. So we just take, because this is already inside this, so whatever is going to, whatever is going to need this would find what it needs in there. So whatever is going to need x minus 1 will find what it needs in x minus 1 squared. So we just pair x plus 1 and x minus 1 raised to the power 2. Then we continue with our work by saying a into x minus 1 squared, okay, plus b into, what's b going to be? Okay, x plus 1. Okay, it's going to take one of these, obviously, because it's going to cut off x minus 1 plus c into, let me just put a big arrow there so that I can slide it up into x minus 1, x plus 1, x plus 1. Then you close it. That is all. That's just all. All right. Then in that case, we know that our denominator, we can see now that our denominator here is the same thing as our denominator here. So it means that our numerators are equivalent. So it means that this implies that 4 minus 2x is actually equivalent to x minus 1 raised to the power 2, a will be here, sorry, plus b into x plus 1, x minus 1 plus c into x plus 1, just like that. Then you just kill whichever way you want to kill, and then your answer will come out. So we know how to kill, so resolve the rest at your leisure. Yes, your leisure. So my signature is here to affirm to that statement. So that is how it is done, and that would bring us to the end of a partial fraction. So I'm going to give you, I'm going to list out, I think I've done that already, but let's just do it again. Let's do it again. I'm going to save this page. Okay, I'm going to save this page. All right. And we'll come to, we'll discuss exercises. So go and look at these exercises. Let's look at these exercises. Resolve the following. Resolve the following into partial fractions. 1, 6x minus 10 over x squared minus 2x minus 3. 2, 4x plus 11 over x squared plus 4x minus 5. 3, x squared plus 4x minus 7 over x plus 1 into x plus 1 into x squared plus 4. That's the third one. The fourth one, 2x4 minus 2x3 plus 4x2 minus 2x over x minus 1 into x squared plus 1. All right, and I think number 5, I think I'm going to give you 5. There are 9, well, there are 10 questions there, but I'm giving you 5 of them. Okay, the 5 should be more than enough. So number 5 should be okay, 2x3 plus 2x2 plus 2 over x plus 1 squared x squared plus 1. All right, so maybe let me just add, since I still have space, let me just add x squared over x plus 1 raised to power 3. This is beautiful. And let me just add let me just add x, that's 7, x cubed minus x squared minus 4 over x squared minus 1. That's the simple one. And lastly, okay, number 8. Lastly, I can have x raised to power 2 plus 2 over x raised to power 2 plus 2x plus 3 times x 2x plus 1. All right. I think I still have the space for one more. High hex, I'm sorry, high hex. That's 7x plus 2 over 2x minus 3 and x plus 1 squared. All right, so that should be more than enough for you. If we take a look at the first one, you see that is a straightforward thing. I think the first one can be factorized. The second one should be factorizable as well. The third one, you can't factorize this guy, so you know that it means that while this one is linear, it's going to be a over x plus 1 plus bx plus c over x squared plus 4. That's what that one is going to be. Likewise, this one, well, this is a repeated denominator. It means, so how many factors are we going to have here? We're going to have x plus 1 as a factor, x plus 1 squared as a factor, and x plus 1 cube as a factor. So we have a, b, and c on top of them. Well, this one can be factorized, this difference of the two squares. Yeah, this one, I don't know, you check it. Then this one has a repeated repeated denominator. So I've practically told you everything you're supposed to do. Please do it, and let's see it when next we meet. We are going to meet online on our WhatsApp group really soon. I would tell you when that will be. All right, so I'm saving this page. Okay, now let's move to another topic. So we have successfully concluded our talk on partial fraction. So let's move to another topic now. Let's look at indices and logarithms. So, but then let's just call it indices for now. Let's call it indices. Indices. So when the time comes for logarithms, we go to logarithms. So we'll quickly look through the laws of indices. I'm sure you're familiar with these laws. Okay. I'm not going to I'm not going to stay too long on the laws. You're familiar with them. So, but then I need to state them all the same. All right. So the first law of indices is A m times A n equals A m plus n. Okay. Just to make it fun, why don't we discuss the reason why this is so? Okay. So that yeah, let's discuss the reason why it is so. Um, well, let's look at example. Let's look at an example. The example would explain to us why it is so. Let's look at, you see, the bases are the same, the powers are different. They are saying when the bases are the same and you are multiplying them, then all you have to do is to select the base, then add the powers. So let's look at base 2 raised to power. No, I don't want to use 2. I want to use something. Uh, I want to use a still. So a raised to power 3 times a raised to power 6. This is what's the meaning of a raised to power 3? That's a times a times a. That's a times a times a. So we are done with this now. This times then a raised to power 6. That's a times a times a times a times a times a. I think 1, 2, 3, 4, 5, 6. Beautiful. So when you look at it, how many ha's do we have? That's 9 ha's. So that's a raised to power 9, which is actually the same thing as when you're saying a raised to power 3 plus 6, which is the same thing as a raised to power 9. So you can now see the reason. So it's not like someone just thought it up and said that I'm going to shove it down your throat, take it like that. No, there are explanations. Like I always tell you, there's nothing in mathematics that you cannot explain. You must be able to explain everything. This is not physics. All right, so this is 1. Now 2. All right, so we have done from a product. Let's look at what we are going to have for division. So if we have a raised to power m over a raised to power n, then it's going to be exactly a raised to power m minus n. All right, which if we base it on the example we did earlier, okay, a raised to power 3 over a raised to power 6 is going to give us, okay, let me set this one as 6 and set this one as 3. Okay, so here is power 3. So it's going to give us a times a times a times a times a times a, everything over a times a times a, isn't it? Okay, if that's the case, so let's cancel out the ones that can be cancelled out. Okay, so the cancellation is done now. So what we have left, we just have these 3. So it's going to be a raised to power 3. So which is the same thing as if we say a raised to power 6 minus 3, which is going to be a raised to power 3. So we don't need to go through that long process again if we know these laws. The laws practically makes our life a lot easier. Okay, let's look at another law. So those are the 2 major laws. Let's look at another law. Let's look at this one, which says, I wish I was actually in the class so that I could test your innovation. Let's look at this one. The third law says a raised to power m multiplying n equals a raised to power m n. Okay, what is it saying is that if you have a raised to a certain power, and that thing as a body is raised to another power, then all you have to do is to just take the product of the two powers and fix it on the base. All right. So let's look at this one as an example as well. I think I'll prefer we do it as an example. Let's look at example. The example would explain the reason why this dude is behaving the way it's behaving. So we have a raised to power 3 times everything raised to power 2. Okay. Now, what is a raised to power 3? I think let's do that one after the other. We know that. So we leave the guy in the bracket first, and we do the guy outside the bracket. So we have a raised to power 3 raised to power 2 is actually a raised to power 3 times a raised to power 2. Do we agree with that? I think we should. Sorry, a raised to power 3. Okay, this is like a square of a raised to power 3, which you have done. So now we can now go further down and look at this guy and expand it. So what's a raised to power 3? That's okay. We actually don't need to do that anymore. We don't need to do that anymore. We can now invoke the first law. Since they have the same basis, the bases are the same, so we can just add the power. So it's going to be a raised to power 3 plus 3, which is going to be a raised to power 6. Now, if we look at this directly, we can see, if we look at it from this one, we can now say, okay, the interpretation of this is that a3 2 equals a3 times 2, which is a6, which is exactly what we have there. Okay, so that is how I'm going to explain the third law of indices. Let me save this page so that we can move on to another law. Uh, don't get me wrong, I know you are familiar with these laws, but then they are saying we should teach you still, so I'm teaching you all the same. Um, is there any other law here? Okay. Okay. Well, let's look at this one. This one, again, don't get me wrong. I don't see any reason why I should teach this course, this particular topic, but I'm teaching it anyway. So, if we have a, if we have a, um, if we have a, I'm coming. Excuse me. Let me pause the video. Let me figure out what is going on. Yeah. So I'm back. Sorry. I was just studying something, so I paused the video. Now it's once. Okay. Now let's look at this law, high V, which says that when you say hey raised to power 1 over n, it is actually the same thing as you taking the fourth root of, the nth root of hey. Okay, and that you'll be wondering, how does that actually make any sense? Please don't mind my snaps. All right, so this is actually quite interesting. So let's look at a raised to power 1 over n. Okay, and we multiply it by another a raised to power 1 over n. Okay, don't let us do that. That's too technical. Let's pick an example. All right. Let me pick an example. Let me scratch this. Let me scratch this. Okay, so I'm gonna pick an example. Okay, don't let me scratch it like that. That's primitive. Let me just delete it from so that it doesn't mess up your the note when I send it. So we now have, say we have a raised to power 1 over 4. All right, a raised to power 1 over 4. We have this a raised to power 1 over 4. Let's multiply it 4 times and see what happens. So this is going to be a raised to power 1 over 4 times a raised to power 1 over 4 times a raised to power 1 over 4 times a raised to power 1 over 4. I think you agree with that, that is actually a possibility. All right, so we applying first rule. If we apply the first rule, we have a raised to power 1 over 4 times a raised to power 1 over 4 times a raised to power 1 over 4 times a raised to power 1 over 4. Okay, let me just turn it away from period to direct multiplication. So this is going to be a raised to power 1 over 4 plus 1 over 4 plus 1 over 4 plus 1 over 4. If you do that carefully, you see that that's going to be a raised to power 1, which is 1. Therefore, what this is saying is that a raised to power 1 over 4 in 4 times is actually a raised to power is actually here. So this is a power here, all right, and this is raised to power 4, which implies that if you are looking for a raised to power 1 over 4, oh sorry, this is going to be 4 because we run it 4 times, not 10. So if you're actually looking for this a raised to power 4 here, you have to take the fourth root of a. All right, so if we generalize it, it means that if we have a raised to power 1 over n, all right, multiplying and raising it to the power of n is actually going to give us a. So if we are looking for just this one, it's going to be a raised to power 1 over n equals the nth root of of a. So I think that clears whatever doubt you have. So example, a natural example now is if we pick um, say 9 raised to power 1 over 2, okay, uh, it's going to give us the root of 9 2, which is going to give us 3. All right, if we select say x raised to power 1 over 3, it's going to be the same thing as the third root of x. Okay, so that's how beautiful that is. Uh, I actually love it. So I'm clearing the page so that I can set up another. Okay, now we can generalize. We call something generalization in mathematics. That is when something that is a normal is made to cover every ground. When you create something that covers every ground from something that is normal. Now let's take a look at this one. This one is interesting. Like I've been saying, these are things you are familiar with, but then this explanation will make it better, I believe. Like, so a raised to power m over n. What does this mean? What does this mean? Um, hmm. How do I explain this one now? Okay, equals. equals mm, uh, a m when you take the nth root of it. Okay, that's what this one is. Okay, when you take the nth root of raised to power n. Now, how do I explain this to you now? Hmm, why not? We use the same technique that we used earlier. So we have the value beneath this one is n, right? So we have, let's look at a m over, let's use numbers. Let's use numbers. So okay, let's use a 2 over 3. Okay, what does this mean? It's a okay. Let's take the product of it over and over. We have um, a 2 over 3 times a 2 over 3 times a 2 over 3. Okay, when we have this, what we are going to have eventually is hmm, a raised to power 2. A raised to power 2. Okay, if you want us to test it, let's test it. We have the LCM will be 3, then it's going to be 2 plus 2 plus 2, which is going to be 6 over 3, which is 2. So what we have done here, okay, okay, let me explain what I've done here. What I've done here is that I've applied the first law, and I have a raised to power 2 over 3 plus 2 over 3 plus 2 over 3. That's the first law. And 2 over 3 plus 2 over 3 plus 2 over 3, that is 2. So it means that this is going to be a raised to power 2. All right. So it actually means that what we actually have there, therefore, is a raised to power 2, 1 over 2. Sorry, 1 over 3. Okay. Sorry, that's not it. Sorry. That's a mistake. I'm sorry about that. Okay. Okay. So we have this to be a raised to power 2. Okay. Yeah, a raised to power 2. Okay. So it means that sorry about that. Sorry about the pause. So let me scratch this one. What will happen is that okay, we have we started with a raised to power 2 over 3. Okay, and we ran it 3 times. That was what we did, and it gave us a raised to power 2. Okay, now to get just a raised to power 2 over 3 out of it, it means that we have to take the cube root of a squared. Okay, so that is exactly what we have here. So let me re-explain this one. So we have a raised to power m over n. Okay, when we run it n times, okay, yeah, we have this one. Okay, um, multiplying it n number of times. So we have multiplying n times. We have a raised to power m over n, everything over n. And then when we run that, it's just going to give us a raised to power m itself. So to get this one out, so it's going to be a raised to power m n, which is what we actually need, will now be, now this is n here, which is the power. To reverse power, you take the root in that power. So a raised to power m. So that. So it's actually quite powerful. We should note it. Thank you for your patience. I'm saving the page again. Let me pause.